Thanks, Lauren. So today I'm really excited to introduce our speaker today, Dr. Matt Hitchings. And we are lucky to have Dr. Derek Cummings joining along for the discussion afterwards. Dr. Hitchings completed his PhD in epidemiology at the Harvard School of Public Health, working with Dr. Mark Lipsitch, who many of you may remember from a previous colloquium talk. And he's currently a postdoctoral associate in the Department of Biology at the University of Florida with Dr. Derek Cummings. And his research uses dynamic disease models to understand how trial design and setting affects the likely success of vaccine trials during outbreaks, as well as working on the design and analysis of randomized trials for the control of infectious diseases. And I'm just going to highlight a few of his findings, noting that a lot of this work is with one of our good friends and collaborators, Steve Bellin, which I was excited to see as I was looking through this work. So Dr. Hitchings has carried out a number of important studies looking at vaccine trial design and how disease outbreak simulations can actually inform trial design. One of those is identifying ways to increase the power and usefulness of cluster randomized trials compared with individual randomized trials. And then also thinking about vaccine trials for some specific disease settings. So for example, during the Zika epidemic, there were really high asymptomatic rates of those infections, as you may remember. And Dr. Hitchings looked at identifying unbiased ways to actually estimate vaccine efficacy for diseases with high asymptomatic rates. And I'm sure there's a number of important implications for COVID-19 vaccine trials from that work as well. And then also looking at, during the Ebola outbreak, understanding how to estimate sample sizes for vaccine efficacy trials using complex trial designs like ring vaccination. So many of you may not be familiar with ring vaccination, but it's a particular trial design where you actually try and identify contacts of index cases and then create your trial from the kind of potential exposures of those individuals. So really interesting and important work looking at vaccine trial design. And in terms of COVID-19, I'm just going to summarize some of the research coming out of the whole Cummings lab. And they have been doing quite a bit of research. I'm going to highlight a couple of their studies where they've used forecasts from models for thinking through how to select sites for vaccine trial design, thinking through, where to plan vaccine trial sites based on where you think incidence will be and kind of this changing dynamic epidemic or pandemic. Also thinking through the impact of non-pharmaceutical interventions. Many of you will also be familiar with their really important systematic review of the immune response to SARS-CoV-2, which I think we've been using for a lot of our work or a lot of informing a lot of our modeling. And then also some really interesting work looking at risk factors for healthcare personnel getting infected with endemic coronaviruses, with some really interesting implications for what types of procedures might be high risk for transmission of SARS-CoV-2 to healthcare workers. And then finally, research led by Dr. Hitchings on the usefulness of SARS-CoV-2 test positive proportion as a surveillance tool, which I believe is what we'll be hearing about today. So with that, I'll let him take it away.
You're muted.
There we go. Can you hear me now?
Yep.
Awesome.
Yes.
Thank you. Thank you very much, Spencer, and thank you everyone for having me to this colloquium speaker series. I'm excited to talk about some of the work that I've done today, focusing on SARS-CoV-2, as Spencer said, the test positive proportion and how it has been used and how it could be used as a surveillance tool to add information to case time series. So I'm going to try, because Derek is here as well, I'm going to try and make this on the quick side, and I will probably fail, but I'm going to try and make it 10 more than 15 minutes to leave time to ask Derek about other projects that we've been doing. So with that, I'm going to present my main rationale, I think can be summarized for this project by this news article from early June in Florida, where we were just starting to see a rise in cases here in the state and also a rise in the test positive proportion. And our dear leader came out and said, well, this is because we are farm workers who are getting lots of infections because they're in close quarters, and that explains why we're seeing more cases, and also why the test positive proportion is going up. And so that was about here on the on the time series, and you can see that that obviously was not what was going on. There was clearly a lot of transmission going on in the whole population statewide. And this is an instance, I think, where a better understanding of the test positive proportion and a better publicly available data on test positive proportions and rates in different populations would have allowed us to untangle the governor's hypothesis versus the hypothesis of every epidemiologist in the state. So to take a step back, what do I mean by the test positive proportion? This is the proportion of tests, or the proportion of people being tested in a place at a certain point in time that return positive for SARS-CoV-2. And it's been being used as a soft or informal indicator for whether a location is doing well or not so well at controlling the epidemic at a certain point in time.
Matt, your audio is coming in and out a little bit.
This happens with my Zoom. I don't know why. Should I? I think I could phone in.
I think we can hear you fine if you just keep your face closer to the screen.
Like this.
No, not that much. It's just every once in a while it sort of seems to go out a little bit. So it's
yeah, this has happened with me before. It's my terrible UF issue computer.
Yeah.
So
we can hear you. It just
buy a new one. Okay. Here's my big face. So the intuition here is that if two places have similar case rates and one place has a lower TPP than the other, that probably means that they are testing more people who are showing fewer symptoms. And that is probably a good thing, because it means bring people who otherwise would not be quarantining. So we're allowing people to know their status, even if they're not showing symptoms. And that kind of makes sense. I think we've seen throughout the pandemic a lot of tracking of TPP with incidence rate. And so people kind of take it as read that this is something you should be interested in. I'm actually not even going to get into why we choose 5% or 3% as our metric for opening. I think that's problematic, but I'm just going to focus on how this could be interpreted alongside case numbers. So the reason I started thinking about this is because I think there are limitations to this logic. It relies on certain parameters driving differences in TPP across time. So this relies on us thinking that, oh, well, we must be testing the right people if our TPP is lower. And it wasn't entirely clear to me that there weren't other things that might affect the TPP that have nothing to do with testing. For example, testing in exposure groups like essential workers or the elderly. What happens if we restrict testing to people over 65, for example? This could definitely drive differences in TPP across time. So what I did was I set up a very simple transmission model, an SEIR compartmental model. I just added testing on top in a mechanistic way using parameters that were well defined, at least within the space of the model. And I was able to derive an approximate relationship between the TPP and confirmed incidence. So the details aren't particularly interesting or important, but I did make, just very quickly, the assumptions that I made were within a certain compartment, your rate of getting tested is determined by whether or not you're displaying symptoms of COVID-like illness, and also if you're in a certain risk group or not. And then the number of tests that are performed every day can be limited by your sort of processing capacity and also by the total number of tests available. And that if there are limited tests, we apply them to the different groups proportional to the demand from those groups. So in the case of limited tests, there's no sort of prioritizing of one group over another, over and above the demand coming from that group. And once I've made these assumptions and kind of written out the model, the model looks like this. Again, not particularly important, but I just wanted to highlight the parameters that are most interesting. So the rate of testing for someone displaying COVID-like illness is one parameter. The rate of testing for someone who's not displaying COVID-like illness is another one. And then there's this proportion of people who are showing symptoms caused by a different pathogen. So I thought this would be interesting. You know, I started this work early in the summer.
Let's see. Maybe he'll join us in a second.
Okay, I'm back. Sorry. I don't know what happened there. I hope you didn't hear me swearing.
We did not. But we've lifted our swearing rules during COVID. So.
Oh, good. So have we in our household. My 3-year-old has fully internalized the meaning of many different swear words. So that's good. Where were we? Yeah, so we have a proportion of people who are coming to get tested because they are showing COVID-like illness who are not actually infected with SARS-CoV-2. So I thought going into the fall, that might be an interesting parameter or an important parameter. And finally, the testing supply is here. And so if the supply is limited relative to the demand, then you apportion the test, like I said, proportional to the demand. And so I was able to work through and derive this relationship between the TPP and the confirmed incidence and the model parameters. And then while I was doing that, I was trying to think of other pieces of information that might be informative within the model. And I was also then able to, in the model, you can easily track the proportion of people being tested who are showing COVID-like illness. And so you can derive a relationship between this test symptomatic proportion and confirmed incidence in a very similar way. So looking at these, I still was not able to see intuitively what these relationships would look like. So I had to plot them, which I did here. So this is a lot of information. So I'm just going to highlight a couple of interesting or important things. So this top panel is the relationship between confirmed incidence and TPP, holding all other parameters constant. So we can see the solid line is TPP, the dotted line is the test symptomatic proportion. So we see a strong positive relationship between confirmed incidence and TPP. So that's what we've seen in data all the time, as well as case numbers go up, the TPP goes up as well. And that's because there's a lot of symptomatic people out there who are seeking testing at a higher rate than.
Sorry, Matt, can you explain what those two lines are one more time?
Sorry, it's at the bottom in tiny writing, very helpfully. So the solid line is just this equation here.
Okay.
And then the dotted line is the test symptomatic proportion. So the proportion of people with COVID-like illness.
Okay.
So as you have higher overall case numbers, you would expect to have higher TPP as well. Because that tracks with infectious prevalence. And obviously, if your infectious prevalence were 1, you would expect your TPP to be 1 as well.
Right.
So the other thing to highlight is these two panels B and C, which are the rate of testing among symptomatic and asymptomatic individuals, and how those look in relationship to TPP. And what we see is if you increase testing in either group, you expect to decrease the TPP, holding other parameters constant. So that kind of lends credence to our intuition that lower TPP is good, because that is an indication that we're doing more testing of people. And so if more testing is associated with more quarantining, that is good. So that's a point for TPP. You know, it adds information if we're comparing 2 places with similar case rates. Yeah.
One question. So on the top right panel, thinking about
Yes.
the rate of testing of symptomatic individuals. So I would have thought that if you're testing more symptomatic individuals, the TPP might go up. So is this because the COVID-like illness? So there are symptomatic people who are not positive with COVID, or how are kind of,
That's a really good question. And I was originally going to explain that and then thought I didn't have time, but now you've answered the question, so now I have to. I had to think this one through. So what's happening here is you're holding the rate of confirmed incidence constant. And so if you're two places have the same confirmed incidence, but one is testing more, they're capturing a higher proportion of actual cases. So there are truly fewer people out there seeking testing. So that is the explanation. Is if the confirmed incidence is higher and you're doing more testing, then the true incidence is actually lower. And so as we see in panel A, that means lower TPP. I think your question then is relevant to the bottom right panel, where if you have more people who have CLI for some other respiratory pathogen, they are going to seek testing at a higher rate, and they'll take tests away from people who are truly infected with SARS-CoV-2. So I think this is a counterexample to the idea that lower TPP is good because it means we're testing better. And so we haven't seen a ton of ILI activity, but my hypothesis going into the fall was that we might see some weird things going on with TPP because of the rise in other respiratory pathogens. And that's not necessarily a good thing. In fact, it's probably a bad thing because it means we're able to capture fewer of the SARS-CoV-2 cases. So we also did some simulations. We simulated some SEIR epidemics just to explore a couple of other things, a couple of other complexities in the model. And we found, so very, very hand-wavily and broadly, we found that if you have different risk groups, like essential workers, or if you have people with comorbidities that you're testing at a higher rate, that does affect your overall test positive proportion. And so my take home from that is if you can possibly break down the data by these different groups, that would be informative, because it would, it would give us more information. And it would allow you to tease out hypotheses about what is driving changes in TPP and confirmed incidence. And then the other thing that we did was we introduced random variation in testing availability, because a criticism of the TPP is that it's very sensitive to changes in test supply or changes in how we test over short periods of time. So we did, we looked at increasing the variability in testing availability, and again, very hand wavy, but the take home from that was we had to work very hard in the model to break this correlation between TPP and incidence in a time series, a modeled epidemic time series. So my take home from that was it should be your strong kind of prior hypothesis that TPP will track with incidence. And so if it's not tracking with incidence, that means that something else is going on. And so that's kind of interesting, and it could be explained by changes in testing. But otherwise, we should expect the two time series to be very strongly correlated. Although having said that, it's much better to look at smoothed, rolling averages, because there can be a lot of day-to-day variability in how labs are reporting and processing their tests. So finally, we looked at a little bit of data just to see what the patterns were like in real data. And so I just picked out, this is data from the COVID tracking project on confirmed incidence and test positive proportion calculated from their data. So the way to interpret this is the solid line is the reported positive tests, and the dotted line is sort of estimated from the TPP. So we just regressed the TPP against the incidence using our equation that we derived earlier it's not really an estimation, but it's kind of an estimated incidence based on what your TPP is relative to other times in the time series. And so the kind of take home from this is it's very clear that in most states, the TPP at the beginning of the epidemic was a lot higher relative to the incidence than later in the epidemic. And that is probably because they were doing a lot less testing. And so there was a lack of supply of tests where it was restricted to people who were more likely to be positive. So in New York and in Michigan, we see this, clearly the TPP was a lot higher earlier in the epidemic than it was later when they're doing more testing. And then in Florida and Arizona, we see this very obvious track of the confirmed incidence with the TPP going up and down in their outbreak over the summer.
With this graph, the dashed lines, is one way to interpret it like the closer the two lines are together, the more reliable TPP is as an indicator of incidence? Is that?
I think it's. I think the interpretation would be there have been fewer sort of changes in testing practices over time.
Okay, and do the lines actually have to match, or do they just kind of have to mirror each other to, as far as?
I think. I don't think you would. That's a good question. I think if they're gonna mirror each other, they're also gonna match in this case. Just so when I say regression, I use the term pretty loosely. It was regression, but as you see in the equation, there were like 10 parameters for what is essentially a straight line. So you're able to kind of get the lines to lie on top of each other if the shape is the same.
I see.
I have one more slide, and I don't know what time it is. Yeah. Some of the recommendations from this are, I think, probably infeasible to be carried out at the state level in terms of the kind of data we would want to collect. But I did think, since I did this work, a lot of colleges have welcomed back their students with open arms, and then some of them have sent them home again. And so I thought that a college campus would be an interesting place where you could conceivably collect and report this data. And the dashboards have been of varying quality across colleges, but they certainly, some of them are reporting potentially the right kind of data. So this is an example from UF. This is not their dashboard, but this is data that was scraped from their daily reports by a professor in another department. So this is the TPP over time for two groups of students, which they were reporting separately. So there were students who were being screened quasi-randomly. I'm not quite sure. It's this return to campus. You get screened one time before you're allowed to interact with other people. And so these people are presumably more likely to be asymptomatic. And then these are students presenting to the Student Health Center who are presumably more likely to be symptomatic. And the interesting thing I think here is that these percent positives are very high. Among these students who are supposedly asymptomatic. We're rolling average of sort of 25% down to 15%, which clearly means that this was not a random sample of students. So I think that to me, this kind of emphasizes the distinction between asymptomatic and symptomatic is probably not enough to present this as a random. It's clearly not enough to present this as a random sample. But there are different ways to cut the data that I think would be more or less informative, and at least separating these two out, I think is useful. But I don't think enough was really done to explain why this was so high. Because if this is truly a random sample of students, that's terrifying. That 20% of students are infected at any one time. Yeah, that was just to say colleges might be a place where you could do some of the things that I'm going to recommend from the modeling work that we did. So my main conclusion about the TPP, which I think is in line with what other people seem to think on Twitter, which is where we all get all our information, is it can be used to identify instances when changes in confirmed cases could be due to something other than changes in transmission. So in plain English, or plainer English, if you're going to claim that a change in confirmed cases is due to increased testing or decreased testing, then you should have the data to back that up with TPP, as long as you have broken it down into the right groups. And if you don't have that data to substantiate that claim, then probably your prior hypothesis will be the most likely one, as we saw in Florida, that increased cases, increased TPP means you probably have underlying increases in transmission. And so recommendations to make it more useful, if you're a lay, if you're just a person on the internet or watching the news, you can't just interpret this as a number on its own. You have to look at it alongside other numbers. You want to look at trends over time, preferably smooth trends, and then where the data permits, if it could be presented in a more granular fashion. For example, by age, or by separating out kind of long-term care facilities and other high-risk institutional settings, that would be very helpful. And finally, more aspirational, if the data on symptom status of people being tested were available, I think that would be very helpful to present that alongside. So finally, I just want to acknowledge my co-authors on this, so Derek, and then postdocs Bingy and Bernardo from Derek's lab, and the grad student Ankana, and Natalie Dean over in biostatistics, and Tom, who's also part of Derek's group, Tom Haddish. And as I said, this is coming soon to AJE, probably not 2020, but probably next year, by knowing the state of play. So thank you very much again for having me, and welcome questions to me. And